Good afternoon, everyone, and welcome to Video Notes 2021. Today I'll be talking about symmetrical projectiles. This is page 17 in the 2021-2022 physics packet. Up until now, we have been talking about horizontal projectiles, that is, an object that travels straight when it becomes a projectile. Most commonly, that's something driving off a cliff. And now we are going to be talking about symmetrical projectiles. That is, things that are thrown straight up and come straight back down. This would be like tossing a pen in the air and catching it. Now, the one thing we will not be covering this semester is asymmetrical projectiles. These are not going to be covered. And these are ones where they are thrown from and land at a different height. This would be like you're throwing something up onto a shelf or dropping something off a cliff. Those kind of things. Now keep in mind I say dropping, not rolling. In general, we're talking about things here that are either been thrown off the edge of a cliff, just rolled straight off that edge, or thrown straight up in the air. Those are the two things we cover in this unit. Now, the free body diagram for any symmetrical projectile is the same for any overall projectile, because a projectile is an object that is only under the influence of the force of gravity. It is that by definition, and so that is the only force that is going to interact with it. Now, symmetry implies equal, and what that means is the time it takes to get to the top of its path, right, over here, here's the way up, the time it takes an object to reach the peak of its path is going to be equal to the time it takes to travel back down. At the top of that object's flight, we need to remember the velocity of it is 0 meters per second. However, the acceleration is still negative 9.8 meters per second squared. The distance that that object travels upwards is going to be the same as the distance that that object travels downwards. Now keep in mind, up is the positive direction, down is the negative direction. And so the way down will be negative. The velocity we throw our object upwards at, on the way up, we'll treat this as v1, and on the way down, we will treat this as v2. We'll be doing calculations for these separately. Now on the way down, here's the velocity we threw it at. On the way down, we will have the opposite velocity when it returns to our hand. So if we throw it upwards at 25 meters per second, it will return to our hand, but it'll be going downwards now, so it'll be going negative 25 meters per second. At the top of the path, our velocity is 0 meters per second, and our acceleration remains negative 9.8 meters per second squared. That is a truth about our planet. Flipping to the back side here, on page 18, keep in mind you can pause if I went a little fast for you on the front page. You can also rewind. We are going to continue to remember this key piece of information that our acceleration is negative 9.8 meters per second squared at the peak of our object's flight, and our speed is 0 meters per second. This helps us out on our data tables here, which are now arranged in terms of the upward motion of the object and the downward motion of the object. On the way up, our velocity is 0 at the peak of our object's flight. On the way down, since we're starting out at the top, our v1 is 0. A remains negative 9.8 meters per second squared in both cases. Now, let's see how this affects a problem that we might have. A baseball is hit straight up into the air. That's one of the ways that we're going to tell you it is a symmetrical projectile. It's in the air for a total of 3.5 seconds. Now, you'll notice that I didn't fill that in for a time value over here. And I'll explain more about that in just a moment. Now, with this baseball, it's hit straight up into the air. It's in the air for 3.5 seconds. We want to know how high did that ball go. That's our question mark. We could figure that out with either the way up or the way down. It's symmetrical, so those values are equal. We do know that at the peak of its flight, it's going to be going 0 meters per second. That means on the way up, it'll be traveling towards that 0 meters per second point. And on the way down, it'll be starting at that 0 meters per second point. Our acceleration will always be negative 9.8 meters per second squared. And now that lets us start doing a little bit of work. If we go and we look through our equations, we might discover that we don't have an equation that has everything we need in it right here, right? I'd be looking and I'd be like, well, I don't know V1, right? I don't know that. I don't even know time. So I might come over here and go, well, I know my total time, but I know that the way up is going to have the same amount of time as the way down. That means half of my total time will be for the way up, and half of my total time will be for the way down. That lets me take 3.5, divide it by 2, and it gives me 1.75 seconds for the time for my trip up, and 1.75 seconds for the time for my trip down. Now, if you're looking at your equations, you'll discover you still have a problem. And that is that you don't have an equation that has x, v2, a, and t in it. However, due to symmetry, I can instead solve for the distance that my ball was traveling in the air by looking at the downward motion. That allows me to use x equals 1/2 at squared plus v1t. I can plug my numbers in. X equals 1/2, a is negative 9.8 meters per second squared. My time is 1.75 seconds. I'll square that. V1 is 0 in this case, since we're starting from the top. And so that 1.75 will go away. Simplify my work. 1/2 of negative 9.8 is negative 4.9. 1.75 squared is going to be 3.0625. And now I'll just multiply those two numbers together. And I'll round that to 15. We're going to see x is going to be negative 15 meters in that case. That was the distance that the ball fell. You can make your answer a little cleaner by flipping the sign, because it would have traveled up a positive 15 meters and fallen 15 meters downwards, negative. Either way, we're going to get 15 meters as our answer, and that's that. Let's look at our one other example here before I am done with this set of video notes. We want to know with what velocity was the ball from number 1 thrown upwards. Well, we know a lot of information now. We know that that ball traveled 15 meters up, and it fell 15 meters down. We know that its velocity at the peak of its flight was 0 meters per second, and at the start it was 0 meters per second when it was going downwards. A is negative 9.8 meters per second squared in both cases, and t is 1.75 seconds for both the way up and the way down. That again, 1.75 plus 1.75 gave us the total of 3.5 seconds in the air. Now, the nice situation I'm in is I want to know what V1 is. And you'll notice I have a wealth of information. When we're in this situation, we can choose any equation that contains the thing we're looking for, because I know all the other numbers. In this case, I find it easy to start with V2 equals V1 plus AT. In this case, I know V2 is 0. V1 is what I'm looking for, so I'll just leave it as V1. A is negative 9.8, and t is 1.75. I'll simplify this work a little bit. Negative 9.8 times 1.75. And I'm going to find that I get negative 17.15 here. 0 equals V1 plus negative 17.15. If I want to get that over here and find out what V1 is, I will add 17.15 to each side of my equation. And I will find that V1 is equal to 17.15 meters per second. All right, your practice problems for this set of notes are on pages 19 and 20. Hopefully this helps. Please email us if you have any questions.